most general form of the equation of motion of a single degree of freedom oscillator occurs in the case of forced vibration for a system with viscous damping. As discussed earlier, the equation of motion is mx double dot plus cx dot plus kx equals f of t. We will not go through the solution methodology in detail, but in general, the solution to the differential equation is obtained by combining the homogeneous solution with the particular solution. The particular solution of the differential equation is a solution that is related to the applied force. As in the case of undamped motion, we will narrow our analysis to the case of harmonic excitation, f of t equals f cosine omega t. Solving for the particular solutions associated with the harmonic excitation results in the first expression in this chart. The particular solution has an amplitude x and is a harmonic function that oscillates at the excitation frequency but has a phase shift which we will denote theta. The expression for the amplitude x and the phase angle are also shown. Similar to the case of undamped motion, the amplitude of the particular solution is a function of the difference between the natural frequency squared and the square of the excitation frequency omega. As expected, the solution is also a function of the damping ratio of the oscillator. Likewise, the phase angle theta is also shown as the damping ratio, the natural frequency, and the excitation frequency omega. Let's examine the key attributes of the amplitude of the particular solution, since this is related to the amplitude of the force response of the oscillator with viscous damping. As we did with the solution for the forced response of an undamped system, let's rewrite the expression so that we can draw out important features of the response. Removing the natural frequency squared from the denominator allows us to write the numerator as f over k, which, as we saw in the case of undamped motion, can be thought of as a quasi-static response since it is equal to the static displacement of the spring with stiffness k for a constant applied force F. For simplicity, we will also write the frequency ratio as R. Plotting the amplitude x as a function of different values of zeta demonstrates the effect of changing the damping ratio on the force response of an oscillator with viscous damping. The effect of damping is negligible when the excitation frequency is much lower than the natural frequency, and the impact of damping is also negligible when the excitation frequency is much higher than the natural frequency. The damping ratio has the greatest impact on the amplitude of the force response in the regime near resonance. Smaller values of zeta lead to larger values of the amplitude at and near resonance. Damping also reduces the amplification of the force response in a region around a frequency ratio of 1. This result has important implications for the effect of damping on vibrating systems. Increasing the viscous damping in a system reduces the amplification of the response near resonance. And for many types of vibration problems, the addition of some form of viscous damping is an important design feature to ensure that the vibration response of the system stays within some prescribed bounds. Now, when we studied the force response of undamped oscillators, we found that the response was unbounded when the excitation frequency was equal to the natural frequency of the system. We note an important difference in the case when the oscillator has viscous damping. As we saw in the plot on the previous chart, increasing the damping ratio leads to lower peak amplitudes of the response at or near resonance. This effect can be quantified by substituting R equals 1 into the equation for the amplitude x. The result clearly demonstrates that the amplitude at resonance is inversely proportional to the damping ratio zeta. As zeta is increased, the peak amplitude at resonance will be reduced, which is consistent with the result shown on the previous chart. Note that this result is only valid for the case of underdamped motion when zeta is greater than 0 and less than 1.